Hi, this is Chrisferb, and I'm going to review a standard normal distribution example, and it's going to be called example 3, I believe, because I've already done 2 other ones. And there's about, I'd say, 5 different ways to do these, or 5 different variants would be, to be more exact. And I'm going to have 5 by the time I'm done. Okay. An item has a mean weight of 70 kilograms and a standard deviation of 15 kilograms. What is the probability the item will weigh 95 kilograms or less? Okay, so the first thing that I always do is I want to write out what I know. And what I know here is a couple things. Okay, so let's do a couple of these. For mu, right here, number one, this is population data, and we have not, think about this as we're not at the point where we're doing hypothesis testing, and this is not a sampling distribution, so it's population data. So the mu for this, which is the population mean, is 70. And then I'm going to go down to the easy one. And then the standard deviation for this is 15. And then the last one, I said I'll go down to the easy one before I go to this other one. Because it says, what is the probability the item will weigh 95 kilograms or less? And so this one's going to have an inequality. So what we say is this item is identified as X, and it's going to be 95 95 kilograms or less, which means it's going to be like this. Less than or equal to, because we said or less, 95. So then the other thing that I always do, working with distributions, and anytime that we are going to have a question of how we do the problem in a picture helps us solve it, I always draw out the distribution. And the picture always helps us solve it with these. Sometimes it doesn't, but with normal distributions, I always recommend drawing out the picture. My drawing's not that good, that's fine. Okay. This is always mu, right, in the middle. And so for mu, it's going to be 70. Okay. So then the next thing that we want to do is we want to figure out where we're going to put our x. And so in this case, our x value right here, 95, it is greater than 70. And now don't look at this part yet right here. Look at this. X is going to be greater than 70 because it's 95. Don't worry about the less than, greater than, equal to, any of that. Just look at x is 95 and mu is 70. So if we look at this and we go out and we look at it like this is a very small number over here, very small value, and this is a very high value over here. So it actually increases as we move to the right and it decreases as we move to the left. Then when we go past mu, which is 70, we're going to go to the higher than mu part. So we're going to go and we're going to put our x right here, okay? Because it's 95. It's 95 kilograms or less. Then we go, whoa, well, what about this or less? So we say, okay, so we start at 95 and then we go or less. So what happens is we end up having this little inequality, and it points to the left. So what happens is we go past mu, and then we look back behind us. And so, so what we do is we write this out, 95. I'm just going to make this, no, that's okay. Okay, so what we have right now, just making sure I have everything there on the picture, right? So now what we have is remember our inequality. We always want it to point towards the area that we're interested in. And then the other thing is, even before that, we want to make sure that we put our x on the proper side of mu. So we put our x on the right side of mu because it's greater than 70. And then we put our inequality on here, and it points towards our area of interest. And our area of interest is everything on the left-hand side of mu. So we kind of do this. Okay. So in this stage, before hypothesis testing or anything like that, we call this the area of interest. In the future, we will call it our rejection zone when we're doing hypothesis testing in that manner. Okay, so now we have everything drawn out. So let's go and do some of our calculations. So what we're going to do, because it follows a standard, in this case, the whole premise of this unit is that it follows a normal standard distribution. So what we're going to do is we're going to do convert everything over to a z-score. And the z-score is always like this. Okay. Make sure everything shows up okay. So we just want to go, remember, and that's x subtract mu over the population standard deviation. So now let's go and put in our actual values, which is 95. Subtract mu, which is 70. Then over 15. Okay. And the answer for this is, for at least what our z-score is, I'm going to run into this, so I'm trying to avoid that, is I'm going to go over here. It is going to be 1.66. So that is our z-score. And the issue is, so that's the z-score. That's our standardized, essentially, number of standard deviations away from the mean, which is mu, or away from the mean, which is fine. So now let's go, and we're going to find on our table our z-score. Now I always use a alternate z-score table, and so I use it for my classes that I do, and your z-table may be different, so it's possible that your figures come up a little bit different depending upon whether you have like a whole table model or a half table model. This is a half table model, and it's not like it comes from the left or the right hand side. It's just half table. And essentially the data comes from, let me back this up. It comes from the middle out on either side, and each side is of course 0.5, 0.5. Okay, for the area under the curve. So we are looking for 1.66. You see it's annotated. I've annotated the heck out of this thing, mainly so that when we move on to confidence intervals and hypothesis testing, I'll show people how all of the annotation stuff works. Okay, 1.6. 1.6. Then we're going to go over to 6. I'm going to move this down so it's a little easier to see. Okay, that'll work. 1.6, 6. So you see, we go from 1.6 out, and then we go up, and it's 6. So when you add this all up, it ends up equaling 1.66. So our answer, which is actually, it's not the final answer, of course. It is the probability under the curve if everything follows this normal distribution, standard normal distribution. It's 0.4515. And it's not, like I said, it's not the answer, but it's just what we're working with. So it's, what was that, 0.4515? Let me make sure. 0.4515. Okay. So this was our z-score right here. And then we go and we actually get the value. And it's 0.4515. Make sure I'm right. Okay. So we're almost ready to solve this whole thing. So this right here, our big question is where this goes. So this is and the big hint for this is um, this is not a whole 0.5 side, right? So usually when we do these problems, if we have a whole side that's not accounted for, which is this over here, this is our 0.5 because it's just the whole thing. And so this side right here, of course, this is going to be over here. So we're going to I'm going to try to navigate this. So this is going to be our 0.4515. My 5 didn't come out that good. Okay, so then we say, well, how do we solve this? What do we do? Sometimes we subtract things, sometimes we don't. In this case, we don't need to do any subtracting because we can just add everything up. If we're looking for this tail portion right here, then we would have to subtract it, because if we added up 0.5 with 0.4515, it would give us exactly what we don't want. But in this case, adding up 0.5 to 0.4515 gives us what we want. So if we add up these two, we get 0.5 plus 0.4515, and I have this already worked out. It equals, actually this one's not hard, it's 0.951. Oh, I almost wrote 4. 5. 9515, and that is our answer. Now, if we were to do this on a calculator, it's possible, it's always possible that it comes up a little bit off when we do it in the calculator, and that's because using the table we only go out 2 decimal places, and it's not always as accurate as the calculator. The calculator's more accurate because it's not picking between just 2 decimal places on the Z table. It actually probably solves it much differently than that. So on the calculator, what we would do is we would go to the dist. Now I'm talking about the TI. Talking about the TI 8384 variant calculator, not the Inspire. It's probably in the Inspire line of the Texas Instruments, but I'm not a huge fan of that. That's okay if you like it. I've just been using the other ones for years. So it's DIST, I believe. DIST, you know what? DISTR. I'll actually do it right here in front of us. So it's DISTR. But we'll just do it. I also have an emulated version, but for this case, we'll just do it right here. Okay, so I'm going to clear it. Okay, I'm going to do second DISTR, and I'm going to zoom in, because when I zoom in, the exposure will be more correct. Okay, so I go and I do second. Let's see, second on my calculator, and then DISTR, and then I can go, and we always do normal CDF in this case. So I'm going to hit enter, and then what we're going to do now on this problem, we were looking at a value that was set with a ceiling value, and then it goes all the way down to everything less than that. So our lower limit is actually going to be 0. If you have a 1, I believe it's negative 1 E99, that's okay. That's the lowest value that you can do. But then I'm going to go and do the upper. So for the upper, we would put 95. I think I checked this problem before I made this. So for the upper, it would be 95. It's already in there. And then for the mu is 70. It's already in there. And then for our standard deviation is 15. It's already in there because, like I said, I checked it. then we hit enter and we get the answer. Now, for this case, as I mentioned, sometimes the calculator is more accurate. Our answer was 0.9515, and this one, now I'm going to zoom back out. This one is 0.9522, and that's okay that it's a little different because we use a table, and the calculator most likely does more of a calculus type of area under the curve calculation for that value. So this was actually 0.9515. So that's our answer, or this is our answer. They're both very accurate. Okay, well, thank you for watching.